Hey, so this is Joe, and we are going to be talking about L'Hopital's rule, and this is the fourth video of the sixth chapter of Stewart's calculus. So I've been talking about this rule, I think ever since the first or second video. This rule is something that makes solving limits a whole lot easier. So this rule, we have a couple restrictions. It only applies to limits that end up being in indeterminate form. An indeterminate form are they're these couple of forms right here. So the indeterminate forms are 0 over 0. So it's an undefined function with a 0 at the top. So it's more than just an undefined function. And plus or minus infinity over plus or minus infinity. So this kind of gives you a hint that all the problems that we will use L'Hopital's rule for are going to be limits that are fractions. So actually, there are limits that look like this. Limit as x approaches a of some function over some other function. And we can only apply this rule to a function where that's indeterminate. So now, what does L'Hopital's rule actually do? Well, it's actually pretty simple, and all you really need to be able to do with it is take the derivative of a function. So the rule states that if we have the limit as x approaches a of some function x over some function g, both in terms of x, and that's indeterminate, so we have this restriction up here, then we can express the same limit as the limit as x approaches a of the derivative of the function in the numerator over the derivative of the function in the denominator. So basically we take the derivative of the numerator and the derivative of the denominator, and then we take that limit. And sometimes when we solve problems, we'll have to apply L'Hopital's rule multiple times in order to get it to work out. Sometimes we'll still need to do a little bit of rearranging like we did before, but this rule makes solving a bunch of limits where you'd have to do a ton of algebra and rearranging a lot easier. Alright, so the first problem that we're going to do is number 15 in your book on page 477. And so we're asked to solve this limit as theta approaches pi over 2 of 1 minus sine theta over 1 plus cosine 2 theta. So first off, when you are solving a limit, same deal. The first thing you want to do is plug in what it's approaching. So 1 minus sine of pi over 2, sine of pi over 2 is going to be 1, so that's 0. And don't put an equal sign here, because when something's in indeterminate form, technically you can make it equal whatever you want, which is why indeterminate forms are so tricky. So draw an arrow or something out here, writing what indeterminate form it's in order to prove that you are allowed, that you're allowed to use L'Hopital's rule and you're not just using it willy-nilly. So when you're doing problems on the AP, make sure to write out this little bit here. So you've got a 0 over, and if it doesn't end up being indeterminate, then we'll just write it down, because then you've solved the limit. And cosine of 2 times pi over 2, so that's cosine of pi. Cosine of pi is negative 1, 1 minus 1, that's also 0. So we've got an indeterminate form, so we can use L'Hopital's rule. So that will equal the limit as theta approaches pi over 2. Now we take the derivative of the numerator, and this derivative, the derivative of sine, is cosine, and so it'll be a negative cosine theta. Now the derivative of cosine is negative sine, so we'll write that out, but you also have to take the derivative of what's inside, so you'll get a 2 out in the coefficient, negative 2 sine 2 theta. And now let's check if we can plug in here and solve the limit this way. So cosine of pi over 2 is going to be 0. Sine of 2 times pi over 2, so sine of pi, is also going to be 0. So we've still got an indeterminate form. So let's try to apply L'Hopital's rule one more time. So we'll get the limit as theta approaches pi over 2. The derivative of cosine is negative sine, so negative and a negative is a positive, so that's sine theta over. And now the derivative of sine is cosine, but we've got a negative, and we'll have to take out the 2, so that'll be negative 4 cosine 2 theta. Now, when we plug in for pi over 2, sine of pi over 2 is 1, so we're looking good. And the cosine of pi is -1, and so negative into negative is a positive, and that's a 4. So we just solved the limit right there. We plugged in. We used the plug-in method, and that means that limit is 1/4. And so that's kind of the most simple application of L'Hopital's rule. L'Hopital's rule is also useful for much more complicated limits, like this one right here. Number 62, again on page 477, this is the most complicated limit, or kind of limit, that you're going to need to solve using L'Hopital's rule, at least on the AP Calculus exams. So this limit, we don't have, it's not a fraction. So already it seems like, well, how are we going to use L'Hopital's rule with this? Well, one test you can do is just do the plug-in method. So e to the infinity plus infinity, that's going to be infinity, because you can't get much bigger than that. And then 1 over infinity, if we make a denominator get really, really big, it starts approaching 0. So 1 over x as x approaches infinity is 0, so we have infinity to the 0. Now this isn't one of the indeterminate forms that we talked about, but it's pretty darn close, and we can actually do some rearranging to this equation using and make it so that it turns into a fraction that will become an indeterminate form, and we will be able to use L'Hopital's rule then. And we're going to be using actually some natural logarithms. We're going to take the natural logarithm of this, and you're going to say, well, how are we going to do that? Well, we're going to make some substitutions. So we're going to call y, that e to the x plus x to the 1 over x. And so this limit here we can also express as the limit as x approaches infinity of y. Great. So we're going to need to manipulate this equation y here in order to get a fraction. And we can do that by using some properties of natural logarithms and logarithms. So we're going to come out here and we're going to take the natural log of both sides. We've seen this before in when we do different differentiation and integration techniques, integration especially. So the natural log of y is going to equal the natural log of e to the x plus x to the 1 over x. And since that exponent is in the argument, we can bring that out as a coefficient. So we got 1 over x ln e to the x plus x. Great. And so that is a fraction. We've got an x in the denominator, and we've got this function in the numerator. Now, let's try to just take the limit with the same parameters here, but take it of the natural log of y. So let's take the limit as x approaches infinity of the natural log of y. We don't need a little line there. And so that'll be this limit, or this function, as x approaches infinity. And when we put infinity into this natural logarithm, we're still going to get infinity. And when we put infinity down here into that x, it's going to be infinity. So we have an indeterminate form. So now we can apply L'Hopital's rule to this function. But bear in mind always that this is not the limit as x approaches infinity of y, or of this function. It's of the natural log of y. And we're going to be able to reverse that later once we find out what this limit is. So here, let's create a little bit of space and write this out again for infinity. And so we're going to continue. We're going to apply L'Hopital's rule here. So we need to take the derivative of this function. So we will get, it's the natural log, so we'll get 1 over whatever's inside, e to the x plus x, and then times the derivative of what's inside here. And that will be e to the x plus 1, and then the derivative of x, that would be 1. Now, and that's the limit as x approaches infinity. And so now we have another fraction here. And let's see if we can plug in for infinity there. Well, we get e to the infinity on top in the numerator. That is infinity. And we get e to the infinity plus infinity. That is still infinity. So we still got an indeterminate form. We're going to need to apply L'Hopital's rule one more time. So the derivative of e to the x plus 1 is e to the x, so that's the numerator. And the derivative of e to the x plus x is e to the x plus 1. and this is the limit as x approaches infinity. And so we seem to be getting close. You know now, if you take the derivative of each side one more time, or each part of the fraction one more time, you'll get e to the x over x, and that'll be 1. So we'll need to apply L'Hopital's rule one more time, because right now we've still got the indeterminate form, infinity over infinity. So we're going to make that application of the rule, and we'll get e to the x over e to the x, and these will cancel, and we'll get the limit as x approaches infinity of 1, and that is just 1. But remember that this 1 is equal to the limit as x approaches infinity of the natural log of y. Ultimately, we want to find the limit as x approaches infinity of y. So we'll have to set the natural log of y equal to 1 to get an expression y equals something. And so we'll use our properties of logarithms. We'll bring the little e that's in the base here over and make the 1 an exponent. So e to the 1, e to the power of 1, that's just e. So then if we were to take the limit, because y equals e, when the limit as x approaches infinity of the natural log of y is equal to 1, that means that the limit as x approaches infinity of y, which is equal to the limit as x approaches infinity of e to the x plus x to the 1 over x, is equal to e. And so that is the most complicated sort of problem that you're going to be solving, at least in these courses, with L'Hopital's rule, and that's kind of how it works. You have to substitute the function in for some other variable, take the natural log of both sides, find the limit of the natural log of the original expression, then get rid of the natural log, and you'll find the limit of the original function that way. So that's the end of Chapter 6, and I think that that's technically the end of Calc AB. So if you're continuing on with BC, keep on going. The next chapter is on advanced integration techniques. It's super interesting. Even if you're not continuing on to BC, it's probably helpful to know. So yeah, thanks for watching, and hopefully you'll stay tuned. Thanks.